All right, let's dive deep into artificial intelligence today. We're going to explore this really complex, fascinating field using a whole range of sources.
We are. We've got academic studies giving that big picture view, industry analyses looking at uses and, limitations.
And we'll also get into the comparisons, the similarities and differences between the human brain and AI.
Plus those really cutting-edge developments in biocomputing and, of course, how artificial neural networks actually work under the hood.
So the mission here really is to give everyone a thorough understanding of AI.
Exactly. From its historical roots through the challenges we're facing right now and looking ahead to what the future might hold.
We'll be touching on the tech advances, obviously, but also the socioeconomic side, the ethical implications too.
It's all interconnected.
For this deep dive, we've got some key sources lined up. There's the study Advances and Challenges of Artificial Intelligence, which gives a great overview, current state, applications, regulations.
And that one draws on others, like Stanford's 100-year study on AI, and books like AI for the Real World and AI the Revolution hasn't happened yet. So a solid foundation.
Then there's the article Brain and Artificial Intelligence, Similarities and Differences, which really digs into those analogies and distinctions, structure, function, how they compare.
And adding a very modern twist, we'll look at that YouTube video, The Role of Human Brain Cells in the Future of AI Bloomberg Primer.
Ah, yes, the biocomputing stuff. Human neurons playing Pong, brain organoids. Pretty wild.
It definitely pushes the boundaries. And to understand the core tech, we'll reference technical descriptions like the Wikipedia entry on artificial neural networks.
And an introduction from Famifa that explains them as mathematical models inspired by the biological brain.
Right, so to really grasp where we are now, we kind of need to look back, don't we, at the history.
Absolutely. The term artificial intelligence itself wasn't coined until, what, 1956?
That's right, the Dartmouth Conference. Marvin Minsky, John McCarthy. They had this, well, pretty ambitious goal of building machines that could actually mimic human intelligence.
But those early hopes hit some roadblocks, didn't they? The tech just wasn't there yet.
Exactly. That led to the first AI winter. Programs weren't performing as expected, like that DARPA language transcription project that failed.
And those predictions, like Minsky thinking in 1970 we'd have human-level general AI in just a few years.
Yeah, turned out to be a bit optimistic, shall we say. Funding dried up, interest waned. It happens.
Then came the 80s and a sort of comeback with expert systems.
Right, systems designed to copy human expert decision-making. But they were expensive, often brittle, prone to errors.
And didn't quite deliver on the hype either.
Pretty much, which led to the second AI winter in the 90s. Another period of disillusionment.
But things were still bubbling under the surface. That last decade of the 20th century set the stage for some big leaps, like Deep Blue.
Ah, Deep Blue beating Garry Kasparov in chess, 1997. That was huge for public perception.
Though it was mainly down to brute force calculation and a massive database of chess knowledge, wasn't it?
It was. Impressive computation, but not really learning in the way we think of it now. It was raw power versus human strategy.
The real resurgence, the current wave, kicked off more recently.
Definitely. You had AlphaGo from Google in 2016 beating Lee Sedol at Go.
Which was significant because Go is way more complex than chess.
Right.
Too many possibilities for brute force alone.
Precisely. AlphaGo used neural networks, machine learning. It learned. That was a paradigm shift from Deep Blue, from explicit programming to learning from experience.
And then AlphaZero took it even further.
Right. The next year. AlphaZero learned chess completely on its own just by playing against itself. No human data, no opening theory.
And it surpassed programs built on decades of human chess knowledge.
Astonishingly, yes. It showed the power of pure machine learning, discovering strategies beyond human experts. The machine wasn't just playing, it was discovering.
So now we're seeing AI spreading everywhere, across almost every sector.
It's moved from being mostly academic theory to practical application. And we're likely only seeing the tip of the iceberg in terms of its potential to transform, well, everything.
Which brings us to the fundamental question. What exactly is artificial intelligence? Defining it is tricky, isn't it?
It really is, partly because intelligence itself is such a slippery concept.
The Royal Spanish Academy definition talks about creating programs that do things comparable to the human mind, like learning or logical reasoning. But as our source notes, that's pretty ambiguous.
Totally. Loads of early computer programs use logic, but we wouldn't call them AI. The difference seems to lie in that human-like ability for complex perception, decision-making, learning.
It's that learning and reasoning analogous to a human mind that seems key.
I think so. And that leads to the distinction between applied AI or weak AI, which is specialized for specific tasks.
Like chess programs or self-driving car systems.
Exactly. Versus generalized AI, strong AI, which could theoretically perform any intellectual task a human can.
And that general AI, that's still firmly in the realm of science fiction for now.
Very much so. Replicating the breadth of human cognition, consciousness, common sense, adaptability is an immense challenge. We don't even fully understand how our general intelligence emerges.
A critical subfield enabling current AI is machine learning, or ML.
Right. This is where systems learn from data to make predictions without explicit programming for every single scenario.
Using statistical methods to find patterns.
Exactly. Finding hidden patterns and relationships in data, then using those patterns to classify new data or make predictions.
Can you give a simple analogy for that learning process?
Sure. Think about teaching a kid what an apple is. You show them lots of different apples, tell them that's an apple. Eventually, they figure out the appleness and can spot one they've never seen before.
So ML algorithms are fed lots of labeled examples.
And they learn the patterns to identify new, unseen examples.
The process usually involves training on data, finding patterns, then using those patterns on new data. An iterative cycle.
Yes, constantly refining based on performance.
But how do you ensure the patterns it learns are real, not just quirks in the training data?
Overfitting, right?
And that's where validation is crucial. You hold back some data the model hasn't seen and test it on that. If it performs well, it suggests it learned general patterns, not just memorized the training set.
And ML algorithms fall into a few main types.
Broadly, yes. Supervised learning, where the data is labeled like the apple example. The algorithm learns the mapping from input to output.
Okay.
Unsupervised learning, where the data isn't labeled. The algorithm has to find structure on its own, like grouping customers based on purchasing habits.
Finding hidden patterns.
Exactly. And reinforcement learning, where the algorithm learns by trial and error, interacting with an environment and getting rewards or penalties.
Like learning to play a video game, getting points for good moves, losing points for bad ones.
Precisely. It optimizes its strategy over time based on that feedback.
And within machine learning, there's deep learning, which has really taken off.
Yes, deep learning uses artificial neural networks with many layers, hence deep, like the diagram in our source material shows. It's been incredibly successful, especially with things like images. What's the key difference from older ML methods?
It's really about those multiple layers. Traditional ML might use simpler models. Deep learning's depth allows it to automatically learn complex features and hierarchical representations directly from raw data. It's particularly good for unstructured data, like images, audio, text.
But it has limitations.
Yeah.
Needs huge amounts of data.
Often, yes,
Right.
especially for complex tasks. And the other big challenge is interpretability.
The black box problem. It's
Yeah.
hard to know why it made a certain decision.
Exactly. The reasoning can be opaque, which is a problem in high-stakes areas like medicine or finance where you need to understand the why.
That lack of transparency must be a hurdle for trust and accountability.
Definitely. There's a lot of research going into making deep learning models more interpretable, but it's an ongoing challenge.
Okay, shifting to the current state of AI science. It's often framed as potentially underpinning a fourth industrial revolution, right? Boosting productivity in R&D.
That potential is huge. Automating complex tasks, optimizing industrial processes, accelerating scientific discovery, enabling mass personalization. The impact could be transformative across many sectors.
What factors really drove this current boom? Better algorithms seem key.
Absolutely. Advances like supervised deep learning and reinforcement learning have allowed models to learn effectively from massive data sets without plateauing too early.
And the open source culture has played a big role too.
Immensely. Sharing code and research findings accelerates progress dramatically. People build on each other's work, ideas spread fast. It's been a huge catalyst.
Then there's the hardware side. Moore's law kept improving processors.
And then came the game changer, GPUs, graphics processing units.
Originally for video games, but perfect for the math involved in neural networks.
Exactly. Their parallel architecture is ideal for the matrix operations deep learning relies on. And then Google developed TPU's tensor processing units, even more specialized for machine learning tasks. That computational power was essential.
And the final piece of the puzzle, data. Just vast amounts of it now.
From smartphones, social media, sensors, everything, data became the fuel for these algorithms. It's now a core strategic asset for many companies.
But that raises issues around data quality, privacy, access.
Huge challenges. Ensuring data is clean and unbiased is critical. Protecting privacy needs strong regulation and tech solutions. And avoiding data monopolies that stifle competition is another major concern.
All this has led to explosive investment, right?
Mm.
Billions flowing to the AI startups.
The numbers are staggering, from maybe $1.3 billion in 2010 to over $40 billion globally in 2020 for AI startups.
And academic interest has surged to publications, PhD students.
It reflects a widespread recognition of AI's transformative potential. It attracts talent, fuels innovation, creates new applications. But, we also need to ask if the investment is always going where it's most needed for societal benefit.
So what are the big advantages machine learning offers? Automation of previously impossible tasks.
Like reliable facial recognition, for example. That just wasn't feasible before ML techniques matured.
And its learning capability can surpass humans in speed and accuracy sometimes.
In specific, narrow domains, yes. Which leads to that interesting idea, the Polanyi paradox.
Ah, right. The idea that we know more than we can tell.
Exactly. An AI might learn to do something incredibly well, like diagnosing certain conditions from scans, without us being able to fully articulate the rules it's using. The machine knows how, but can't explain it in human terms.
ML is also changing work, automating routine tasks.
Freeing up humans, hopefully, for more complex creative or interpersonal work, though that transition needs careful management.
And optimizing business operations, like Amazon using it for inventory management.
Yes, or using robots in their warehouses for logistics. These are substantial changes to how businesses run.
And even redefining business models entirely.
Yeah.
Recommendation engines on streaming platforms, for instance.
Absolutely. Using user data to personalize offerings creates immense value, sometimes becoming a revenue stream itself. We'll likely see more disruptive models based on hyper-personalization or predictive analytics.
Okay, let's get into specific applications. We can group them into perception and cognition. Perception's about sensing the world. Voice recognition is a big one.
Huge improvements there. Accuracy is much better, making voice assistants genuinely useful. The market for them has exploded.
What drove those improvements? Deep learning again.
Largely, yes. Techniques like recurrent neural networks and transformers are much better at handling the nuances of human speech, background noise, accents. It makes voice interaction feel more natural.
Image recognition is another perception powerhouse, used everywhere now.
And making a massive impact in medicine, right? Analyzing medical images, lab samples.
Helping detect diseases earlier, like cancer, or even tracking pandemics like COVID-19 from chest scans.
It's augmenting the capabilities of doctors, helping them process vast amounts of visual data more efficiently and accurately. But getting enough high-quality, privacy-protected medical data is a challenge.
Autonomous vehicles are another perception-heavy application, processing sensor data incredibly fast.
Optimizing driving using real-time network info like traffic, weather, pedestrian detection error rates have plummeted.
Still, widespread adoption seems a way off. What are the main hurdles?
Safety is paramount, ensuring reliability in all conditions, handling unexpected edge cases. Then there's regulation, public acceptance, infrastructure, and those tricky ethical dilemmas in accident scenarios.
Facial detection, too. Unlocking phones, tagging photos, even detecting emotions now.
But that raises major privacy flags, especially with widespread surveillance uses in some places. Finding the balance between innovation and privacy protection is critical.
These clear rules may be privacy-preserving techniques.
Exactly. And public debate about where we draw the lines.
And then there are GAN's generative adversarial networks, creating realistic fake images, text to image.
Amazing creative potential generating game worlds, artistic styles, but also the risk of deepfakes.
Like those convincing fake videos.
Right.
That makes distinguishing real from AI-generated content really hard.
It does. It undermines trust in information. We urgently need better detection tools and better media literacy to combat disinformation fueled by this tech.
Okay, moving to cognition processing data, creating knowledge, natural language processing, NLP.
This is about enabling human-machine interaction through language. Chatbots, machine translation, sentiment analysis.
Summarizing long texts, even assisting with writing code now. How is this changing how we interact with tech?
It's making it more conversational, more intuitive, getting customer service from a chatbot, instantly translating web pages, understanding customer reviews at scale. It removes friction.
Games have always been a testbed for AI, haven't they?
From Deep Blue to AlphaGo and beyond, AI excels in complex games like poker or StarCraft 2 now. Chess engines are standard training tools for humans.
What do these game successes tell us about intelligence?
They show AI's power in learning complex strategies, adapting, making decisions in vast possibility spaces. It highlights the strength of machine learning and reinforcement learning for tackling hard problems.
Finance is another big area. Fraud detection, credit risk assessment.
Algorithmic trading, robo-advisors offering automated financial advice, even optimizing traffic lights in cities using AI.
Improving efficiency and security across the board.
That's the goal. Detecting fraud patterns humans miss, making faster trading decisions, reducing traffic congestion.
And robotics. Automating physical tasks is progressing, but humanoids are still tricky.
Yes, automating structured tasks in logistics, like Amazon's warehouse robots, is happening. But creating general-purpose humanoid robots that can navigate and interact safely in complex, unstructured human environments is still a major research challenge.
Other big applications, recommendation systems everywhere. AI and the Internet of Things for smart homes and cities.
The list keeps growing. AI is becoming deeply embedded in the digital infrastructure.
Despite all this progress, AI faces significant challenges. Generalization is a big one.
Right. AI systems are often very specialized. Their performance can drop dramatically if the data they encounter is different from their training data. Achieving broad, human-like general intelligence is still far off.
How are researchers trying to improve generalization?
Things like transfer learning, applying knowledge from one task to another, or multitask learning, and developing models that are inherently more robust to variations in data.
And the need for vast amounts of data for deep learning? That's a limitation too.
Especially in fields where data is scarce or expensive. Research into few-shot learning training models effectively with much less data is crucial. Data augmentation or synthetic data generation are other approaches.
Robustness is another issue. These systems can be brittle, vulnerable to adversarial attacks.
Yes, tiny, almost imperceptible changes to input data can sometimes fool an AI system into making big mistakes. Think of slightly altered road signs confusing an autonomous car.
That's a serious security concern for real-world deployment.
Absolutely. Making AI systems resistant to such manipulations is critical for safety and reliability.
AI also lacks common sense, right? That intuitive understanding of how the world works.
It does. It doesn't have the embodied experience or the vast background knowledge humans use effortlessly. It also can't really set its own goals or be genuinely curious. It's a tool executing specific tasks.
Do you think AI will ever develop something like common sense or curiosity?
That's the million-dollar question. It's incredibly hard to replicate that intuitive grasp of the world we gain through living in it. Maybe we'll see progress in learning richer world models, but true curiosity and autonomous goal setting seem very distant.
And we mentioned the black box problem earlier, the lack of interpretability.
Which hinders trust, makes debugging hard, and prevents us from learning from the AI's insights sometimes. Work on explainable AI, XAI, is trying to address this.
What kind of techniques are used for XAI?
Things like identifying which input features were most important for a decision, using simpler, inherently interpretable models where possible, or building systems that can provide some form of justification for their output.
Public trust is another hurdle. People often feel uneasy about AI, even if it's statistically safer in some cases, like autonomous driving.
It's true. There's often more tolerance for human error than machine error. Building trust requires transparency, demonstrated reliability, clear communication about limitations, and involving the public in discussions about deployment.
And what about soft skills? Empathy, persuasion, motivation, things crucial for teaching, leadership, care work. Can AI learn those?
That's extremely difficult. These skills are deeply tied to human emotion and social understanding. There's a real risk of dehumanization if we replace human interaction with algorithms in sensitive areas like healthcare or education without careful thought.
So the focus should be on AI augmenting human capabilities in these areas.
Ideally, yes. AI is a tool to support professionals, handling data analysis or routine tasks, freeing up humans for the essential person-to-person interaction.
Improving human-machine coordination is key then, since most applications involve collaboration.
Building mutual understanding and trust between humans and AI systems is vital for effective teamwork.
And finally, the resources needed, hardware, software, skilled data scientists, aren't evenly distributed.
No, there's a skills gap and an access gap. Democratizing AI requires investment in education, open source tools, cloud platforms that lower barriers to entry, and policies promoting wider access.
Looking ahead now, what does the future hold? Technologically, more deep learning proliferation.
Almost certainly, fueled by ever-increasing data. NLP is also set for rapid development understanding customers' market analysis.
What other algorithmic breakthroughs might be on the horizon?
We could see advances in reinforcement learning for more sophisticated autonomous agents, better generative models, and perhaps more integration between different AI approaches, like combining symbolic reasoning with deep learning.
And new computing paradigms.
Yeah.
Neuromorphic computing.
Inspired by the brain's efficiency, yes. Still early days economically, but potentially much more energy efficient for certain tasks.
And quantum computing.
That's a longer-term prospect, but it could potentially solve problems currently intractable for classical AI, maybe in drug discovery or material science. Could be revolutionary if it scales.
What about new applications? Health seems like a major area for transformation.
Assisting diagnosis, automating data analysis, robotic surgery, personalized health monitoring, tools for people with disabilities, even advanced algorithms for social interaction support. The potential is vast, though again, we must avoid dehumanizing care.
Human-machine collaboration will likely deepen across many fields.
AI assisting with complex analysis, decision support, handling information overload, acting as intelligent assistants.
What about areas we can barely imagine now?
Maybe breakthroughs in fundamental science driven by AI analyzing complex data sets, tackling climate change modeling, designing novel materials, even aiding space exploration. Its ability to find patterns in complexity could open new frontiers.
But we also need to be mindful of the risks, starting with short-term ones. Over-reliance on AI.
Trusting it too much, underestimating its limitations, leading to poor decisions based on flawed algorithms.
And discrimination. Algorithms inheriting biases from data.
A huge concern. If training data reflects historical biases, AI can perpetuate or even amplify them in critical decisions like hiring, loans, or criminal justice.
Potentially worsening inequality.
Exactly. How do we mitigate this? We need robust ethical frameworks, transparency, auditing for bias, diverse development teams. It requires constant vigilance.
Other short-term risks. Data monopolies limiting competition.
Yes. And potential slowdowns in hardware progress, like Moore's law tapering off, might require new computing approaches.
Privacy concerns will only grow with more data collection.
The risk of breaches, misuse of personal data, excessive surveillance, balancing data use with privacy rights is a major ongoing challenge.
And the threat of manipulation and disinformation. Deepfakes, targeted propaganda.
Very serious. AI makes creating convincing fakes easier and cheaper and enables hyper-personalized manipulation online. We need technical solutions for detection and societal solutions like media literacy.
What about the longer-term risks, the existential stuff about artificial general intelligence, AGI?
The idea of superintelligence surpassing human control. While most experts think true AGI is still very far off, or maybe impossible, it's a conversation worth having now.
Like the concerns raised about autonomous weapons.
Exactly. The open letter from researchers calling for a ban highlights the need for proactive ethical discussion and regulation around potentially dangerous AI applications, even before they fully materialize. Thinking about safety and alignment early is prudent.
A really intriguing tangent is this idea of biocomputing using living brain cells for computation.
Like the Cortical Labs experiments with neurons playing Pong dish brain, or Final Spark offering access to brain organoids on their neuro platform.
Trying to harness the brain's processing power directly. What's the potential there for AI?
Well, the brain is incredibly energy efficient compared to current AI data centers, which consume vast amounts of power. Biocomputing might offer a path towards more efficient, perhaps fundamentally different ways of processing information.
But it faces huge engineering challenges, right?
Yeah.
Keeping cells alive, scaling it up, interfacing with electronics.
Massive challenges. Powering them, waste removal, temperature control, limited lifespan, integrating with hardware. It's a very early stage research, but the investment is happening.
And beyond AI, there's potential for understanding the brain itself. Neurological diseases.
Absolutely. Using organoids or brain-on-a-chip models could revolutionize how we study brain development, test drugs for conditions like Alzheimer's or Parkinson's, or understand toxicology effects, as Thomas Hartung is exploring. That medical potential is immense.
Finally, let's circle back to the core technology, artificial neural networks, ANNs.
The mathematical models inspired by the brain's structure neurons, synapses that underpin much of modern AI, especially deep learning.
They take inspiration from biological neurons, the soma, axon, dendrites, synapses, but are they very close replicas?
They're highly simplified analogies. An artificial neuron gets inputs, multiplies them by weights, like synapse strength, sums them up, maybe adds a bias, then passes the result through an activation function to produce an output.
That activation function is key, isn't it?
Yes, it introduces nonlinearity, allowing the network to learn complex patterns beyond simple linear relationships. Without it, even a deep network would just be equivalent to a single linear layer.
And training these networks involves adjusting those weights.
Exactly, using algorithms like backpropagation and gradient descent to tweak the weights iteratively, minimizing the error on the training task until the network performs well. Like finding the right slope for a line separating different data points in that simple perceptron example from our sources.
They can have multiple layers, input, hidden layers, output, allowing them to tackle more complex problems.
Right. And their history had ups and downs too. Early promise, then Minsky and Papert's critique highlighting limitations, leading to a quiet period.
Before the resurgence from around 2006 onwards, driven by better algorithms, more data, and that crucial hardware like GPUs.
Correct. Now we have many types of ANNs, complex architectures used in deep learning for things like semantic hashing or memory networks.
But overfitting remains a challenge. The network learning the training data too well, but failing on new data.
Yes, it's a constant concern. Techniques like cross-validation testing on multiple subsets of data and regularization, adding penalties for model complexity, are essential to help the models generalize better to unseen data.
So wrapping up this deep dive, AI has come an incredibly long way, from theory to a truly transformative force.
Driven by algorithms, hardware, and data. But significant challenges remain generalization, transparency, trust, ethics.
And these explorations into biocomputing and the continued evolution of neural networks offer fascinating, if complex, future paths.
Which leads to a final thought for our listeners. As AI gets more integrated into our lives, what's the right balance between AI-driven automation and the unique roles of human intelligence and capabilities?
And what social or ethical implications worry you most as this technology keeps developing? Lots to think about.
Definitely. We encourage everyone to keep exploring this dynamic field. Understanding it is crucial for navigating the future AI is shaping.